In the previous lecture, we have seen the problem of superposition of two collinear simple harmonic oscillations of equal frequencies. But today we will see what will happen when we will consider the superposition of two collinear simple harmonic oscillations of different frequencies, not equal frequencies. Actually, you will see when the superposed harmonic oscillations are not of equal frequencies, then we will get something different result. And in this condition, you will also see or you will also learn about a very important phenomenon occurring in case of waves and oscillation, that is called the phenomenon of bits. Particularly, this phenomenon of bits is a most important phenomenon in case of waves, particularly sound waves, which we will see later on. But how the concept of bits arises, what are these bits, we will learn in this lecture. In fact, you will see that when the superposed oscillations have frequencies slightly different from one another, then bits occurs. If the frequencies of the superposing oscillations are very different, their difference is large, then bits cannot take place. But whenever the difference in frequencies of the two simple harmonic oscillations is not very large, it means the frequencies of the superposed oscillations are almost equal, then you will see this particular phenomenon of bits occurs. Okay? So now let us analyze this problem of superposition of two collinear simple harmonic oscillations of different frequencies. And for this, as we have seen earlier, we have shown in this figure that this is an oscillator, or you can say an object which is acted upon by a restoring force F1, as you can see in this first figure. And under this restoring force F1, this object or this oscillator performs harmonic oscillations, or you can say simple harmonic oscillations. Okay? And I have assumed that at any moment t, x1 is the displacement of this oscillator from its equilibrium position, and a1 is the amplitude of oscillation, and this oscillator oscillates with an angular frequency omega 1 under this restoring force F1 acting along the x-axis. Okay? But when the same oscillator is subjected to another restoring force, let us say F2, removing F1, then again this oscillator will perform simple harmonic oscillations along the x-axis. And I have shown in this figure that x2 is the displacement of the oscillator at any moment t, and a2 is the amplitude of oscillation, and omega 2 is the angular frequency of this oscillation under the restoring force F2. Okay? Now we will see what will happen when both of these restoring forces F1 and F2 will act upon this oscillator simultaneously. So in this third figure you can see I have shown both F1 and F2 acting on this oscillator simultaneously. Okay? In this condition, what will be the displacement of this oscillator at any moment t? That can be found by using the superposition principle, as we have learned in my earlier videos. So if you assume that x is the displacement of this oscillator under the restoring force F1 plus F2, then in accordance with superposition principle, you know x will be simply equal to x1 plus x2. This is in accordance with the superposition principle. Okay. Actually, when these two oscillations will get superposed, a resulting oscillation is produced, and that resulting oscillation is called modulated oscillation. This is the process of modulation, and the resulting oscillation is called modulated oscillation. And whenever you will talk about two waves instead of oscillation, then we will say that after the superposition of two harmonic waves, a resulting wave will be produced, which is called modulated wave. Okay? And we consider that this AM is the amplitude of this resulting modulated wave. Okay? And what will be the frequency of this modulated wave, we will see now. Okay? Actually, you will see that this wave will almost travel with a frequency which is just the average value of this omega 1 and omega 2, but only when omega 1 and omega 2 will differ by a very small amount. Okay? We will see later on. Okay? So now let us try to find the modulated oscillation. Okay? After the superposition of the two individual harmonic oscillations acting on an oscillator in the same on the same line. Okay? So let us analyze this problem in analytical way or mathematical way. As you have seen, we have assumed that x1 be the displacement of the moving part of our system at any moment t under the restoring force F1. Since under the restoring force F1, this particle or this oscillator or this object will perform simple harmonic oscillation. So you may write the expression for x1. You know that simple harmonic oscillation may be expressed as in terms of a cosine function or sine function or in terms of exponential function. I have written here the value of x1 in terms of cosine function. You also may write in terms of sine function. So I have assumed that x1 is equal to a1 times cosine of omega 1 t plus phi 1. You know here a1 is the amplitude of this oscillation and omega 1 is its angular frequency. And what is this phi 1? You know, phi 1 is called phase constant, or it is called initial phase. That is, when t will be 0, then phase will be equal to phi 1. So phi 1 is also known as initial phase. So this is the equation of motion of the oscillator oscillating under the restoring force F1. Okay, acting on the system in x direction. Now, when you apply the restoring force F2 on the same oscillator, removing F1, then displacement of the oscillator at any moment t, we assume it is equal to x2. And that x2 on the similar way you can write is equal to a2 times cosine of omega 2t plus phi 2. Here you can say that this A2 is what? This will be the amplitude of this second oscillation, and omega 2 is its angular frequency. And phi 2, this is initial phase or phase constant of the oscillation taking place under the restoring force F2. But our prime aim is to discuss the problem when both of these oscillations will get superposed. And for this you can see the situation in this third figure, where I have shown that both of the restoring force F1 and F2 have been acted upon on this oscillator simultaneously. Okay? So if you consider that x is the displacement of this oscillator when both of these oscillations get superposed, then in accordance with superposition principle, you know that resulting displacement x will be given by x1 plus x2. This is in accordance with the principle of superposition. Now, let us substitute the value of x1 and x2, which we have written above. So, instead of x1, now you can write a1 times cosine of omega 1t plus phi 1 plus a2 times cosine of omega 2t plus phi 2. Okay. Actually, here, for simplicity, we assume that the two oscillations have the same phase constant and which may be taken to be equal to 0 for simplicity. It means we will take phi 1 is equal to phi 2 and that is equal to 0. This is for the sake of simplicity. But if you will take phi 1, phi 2 both equal to 0, then it will make any difference in our concept? Answer is no. If you will take phi 1, phi 2 non-zero, even different, even then the result obtained, and when you take phi 1, phi 2 both equal to 0, then the result obtained will be identical. It will not make any reasonable physical sense of any different concept. In fact, we could take the initial phases to be of different and non-zero, but it turns out that a finite initial phase difference only adds to the mathematical complexity and is in general not of major significance in this present case. So in this present case, our physical result will not be affected when you will take both phi 1, phi 2 equal to 0. So for the simplicity or for the less rigorousness of mathematical complexity, we take both phi 1 and phi 2 equal to 0. And therefore, you can see x will be given by a1 times cosine of omega 1t plus a2 times cosine of omega 2t. Okay. Now, to simplify the RHS of this equation 1 or to recast this result in a suitable form, we will define two quantities. First of all, we are going to define a frequency denoted by the symbol omega A, which is actually called the average frequency. This is called average frequency. Okay. Here the subscript A has been written for the word average. And since omega 1 and omega 2 are the individual frequencies, so their arithmetic mean will be equal to omega 1 plus omega 2 over 2. So we define omega A as omega 1 plus omega 2 over 2. Now, you know, when the two oscillations will get superposed, a resulting oscillation will be produced, which is called modulated oscillation, and we assume that this modulation frequency omega m is equal to omega 2 minus omega 1 over 2. Omega 2 minus omega 1 over 2. Instead of this, we write omega m, which is actually the modulation frequency. Okay. Now, on the basis of these two assumptions, we can find the values of omega 1 and omega 2 in terms of omega A and omega m. Okay. In terms of omega A and omega m, you can find the values of omega 1 and omega 2, which are actually the frequencies of the individual oscillations. And you can see that if we will find omega A minus omega m, what will be its value? Since omega A, you can see it is omega 1 plus omega 2 over 2, and omega m is omega 2 minus omega 1 over 2. Here, this omega m has been defined in the manner omega 2 minus omega 1 over 2 on the basis of the assumption that omega 2 is greater than omega 1. If you will assume that omega 1 is greater than omega 2, then you should take here omega m equal to omega 1 minus omega 2 by 2. But since our assumption is omega 2 is greater than omega 1, so we take omega m equal to omega 2 minus omega 1 over 2. Okay. Now, what will be omega a minus omega m? As you have seen, we are going to calculate it. So let us put the value of omega a and omega m from here in this expression. And you can see this will be omega 1 plus omega 2 minus omega 2 minus omega 1 over 2. Now, when you will remove this bracket, then this omega 2 will cancel out and omega 1 will be added up. So this will be 2 omega 1 over 2, and that is simply equal to omega 1. So you can see omega 1 in terms of omega a and omega m can be written as omega a minus omega m. Okay. Now, in the similar manner, when we will evaluate omega a plus omega m, what will be our result? This will be omega 1 plus omega 2 plus omega 2 minus omega 1 over 2. Here this omega 1 and this omega 1 will cancel out, and this will be 2 omega 2 over 2, and that is equal to omega 2. So omega 2 is equal to sum of omega a and omega m, and omega 1 is equal to difference of omega a and omega m. Now let us substitute the values of omega 1 and omega 2 which we have obtained here in terms of omega a and omega m in our equation number 1. Okay, let us put it instead of omega 1 and omega 2. Let us see. So x now can be written as a1 times cosine of omega 1t, but instead of omega 1 we will now write omega a minus omega m. Okay, and plus the second term is a2 cos omega 2 into t, but you can see omega 2 is equal to omega a plus omega m. So the second term is a2 cosine of omega a plus omega m times t. Okay. Now we will expand both of these cosine terms by using the formula of trigonometry. Cos a plus b is equal to cos a times cos b minus sin a times sin b. Using this formula, you can write this cos omega a minus omega m times t as in this manner. This is cos omega a t times cos omega m t plus sin omega a t times sin omega m t. Okay? And in the similar manner, cosine of omega a plus omega m into t will be what? That is equal to cos omega a t times cos omega m t and minus sin omega a t times sin omega m t. Okay. Now let us see. When you will select the first term of this first square bracket inside the first square bracket and the first term inside the second square bracket, then you can see this cosine of omega a t times cos omega m t. This is a common factor, and the remaining term will be a1 plus a2. So the first term can be written as a1 plus a2 times cos omega a t times cos omega m t. Okay. Now see the second term inside the first square bracket and also inside the second square bracket. in the second term you can see this sine omega at times sine omega mt can be taken as a common factor, and the remaining terms will be, I have taken here minus sine as a common factor, so this will be a2 minus a1. Okay. Now to recast this equation in a simpler form, we assume that this a1 plus a2 cosine of omega mt is equal to am times cos delta m. We assume it. And a2 minus a1 times sine of omega mt is equal to am times sine delta m. Here am and delta m both are actually unknown. These are not known. Am is the amplitude, this is actually the amplitude of the modulated oscillation, and delta m, you will see this will be the phase constant of the modulated oscillation. You will see later on. But before that, let us substitute these values in equation number 2. So instead of a1 plus a2 cos omega mt, we will write this much, am cos delta m. And instead of a2 minus a1 times sine omega mt, we will write this much, am sine delta m. After substituting these, this equation 2 will become like this, x equal to what? This is am times cosine of omega at times cos delta m minus sine omega at times sine delta m. But you can see the expression inside the square bracket can be written as cosine of omega at plus delta m. So finally we get that the resulting oscillation can be represented by the equation x equal to am cosine of omega at plus delta m. Okay. Actually, when you see this equation, particularly equation number 5, definitely this equation just resembles with the equation of SHM. You know, you write the equation of SHM in this manner, x equal to a cos omega t plus delta. So both of this equation resembles with the equation of SHM. So you can get confused that x is a simple, here equation 5 represents a simple harmonic oscillation. But actual situation is not like that. In fact, you will see that this equation x equal to am cos omega at plus delta m, this is just its resemblance with equation of SHM is just misleading. It does not represent a simple harmonic oscillation or vibration. Why it does not represent a simple harmonic oscillation, you can see. Actually, in this equation, as you can see, am and delta m are arbitrary constants which we have assumed here, but their values are not known. So now, let us try to find the values of am and delta m. You can look equation 3 and 4. Actually, if your aim is to find am, then you must eliminate delta m. And for this, let us square equation 3 and 4 and add them. When you will add equation 3 and 4 after squaring, you will get the value of am. And you can see this will be am square equal to a1 plus a2 whole square times cos square omega mt plus a2 minus a1 whole square times sine square omega mt. Now, here you can see there will be the first term will be a1 square times cosine square omega mt. Okay, and in this second term there will be also a1 square times sine square omega mt. In those two, when you will combine those two terms, you can take this a1 square as a common factor, and the remaining term will be cos square omega mt plus sine square omega mt. Then again see, the first term will contain a2 square times cos square omega mt, and the second term will contain a2 square sine square omega mt. So again we will combine those two terms containing a2 square, and that will be a2 square times cos square omega mt plus sine square omega mt. Okay. Then in the first term there will be a term 2a1 a2, okay, and cos square omega mt. Okay. And in the second term you will have 2 minus 2a1 a2 sine square omega mt. Okay. And when you will combine these two terms, then this 2a1 a2 can be taken as a common factor, as you can see it here, and the remaining terms will be cos square omega mt minus sine square omega mt. Okay, I think you have clearly understand the algebra here. Now you know this is 1, this is also 1, and what is this? You know, cos square theta minus sine square theta is equal to cos 2 theta. So utilizing those formula, you can see am square will be simply equal to a1 square plus a2 square plus 2a1 a2 cosine of 2m omega t. Okay? And therefore am is equal to a square root of a1 square plus a2 square plus 2a1 a2 cos 2 omega t. Okay? So this is the value of am in terms of a1, a2 and the modulated frequency omega m. Okay. Now we will find the value of the unknown quantity delta m. Again see equation 3 and 4. If your aim is not to find delta m, you have to eliminate am, because am is also unknown. And for this, let us divide this equation 4 by 3. Equation 4 by 3, we will divide. And you can see, when you will do it, you will get tan delta m equal to a2 minus a1 sine omega mt over a2 plus a1 cos omega mt. Now, sine omega mt over cos omega mt, this can be written as tan omega mt. So, tan delta m is equal to a2 minus a1 over a2 plus a1 times tan omega mt. So, using equation 6, you can find the unknown am, and using equation 7, you will be able to find delta m. But let us see equations 6 and 7 seriously. Can you say that am and delta m are constants? Answer is no, they are not constant, because you can see this am varies with variation of time t. It is time dependent. Similarly, this delta m is also time dependent. So with change in time, the values of am and delta m both will vary, both will change. So now let us see. In equation 5, since am and delta m are time dependent, they are not constant. So the formal resemblance of this equation with the equation of simple harmonic motion is misleading. In fact, the oscillation described by this equation 5 is not harmonic because the amplitude am and the phase constant delta m both vary with time. They are not time independent. If am and delta m will be time independent, they do not depend on time, only then you can say that this equation 5 will represent a harmonic oscillation. But in our calculation you can see both am and delta m are functions of time, they will vary with time, and therefore although form of this equation 5 is just like the equation of SHM, but in fact in actual sense, due to the time dependence of am and delta m, this equation does not represent a harmonic oscillation. Okay? In fact, this oscillation can at best be described as periodic with angular frequency omega a, which is actually the average of the two component frequencies. Okay? So this equation 5 does not represent a simple harmonic oscillation. So what we actually obtained here, when two simple harmonic oscillations of unequal frequencies are acting on a body or are superposed, then we do not get a resultant, then the resulting motion in general is not simple harmonic. Okay? The resulting motion is not simple, although the motion will be periodic and the frequency of that periodic motion will be just the average value arithmetic mean of the frequencies of the superposing oscillations. But the resulting oscillation is not simple harmonic, but it is only periodic. I have told you in my previous videos that all periodic motions or all oscillatory motions are not simple harmonic motions. So when omega 1 and omega 2 are different from one another and their difference is also very large, in that condition, after the superposition of two simple harmonic oscillations which are collinear, we do not get a simple harmonic oscillation. This is a very remarkable fact, very interesting fact. Okay? But what will happen when omega 1 is not very different from omega 2, or in other words you can say when omega 1 and omega 2 differ from one another slightly, they are almost equal, then what will happen? Actually, then you will see when the frequencies of the superposing oscillations are very close to one another, then after superposition we will get a simple harmonic oscillation. Then you will get a simple harmonic motion. But as long as omega 1 and omega 2 will be far different from one another, then you will get only a periodic vibration, not a simple harmonic oscillation. But when omega 1 and omega 2 will be close to one another, although different but close, the difference is not very large, then you will see that actually the resulting motion will be also simple harmonic. And in this condition, a very important phenomenon occurs, that is called bits. So now our aim is to discuss the phenomenon of bits in waves and oscillation. Okay? Here we will discuss these bits only in case of oscillation, but when we will start to learn about waves, particularly sound waves, then you will again see the problem of bits. Actually, this problem of bits is very important problem of wave motion. Okay? So I have mentioned it here. You can see when omega 1 is almost equal to omega 2, that is the two frequencies differ slightly, then resulting oscillation exhibit the phenomenon which is known as bits. Okay, and in this condition you can see when you define that this omega A is omega 1 plus omega 2 by 2 and omega m is omega 2 minus omega 1 by 2. Okay, so since omega 1 is almost equal to omega 2, so you can see that this omega m will be very small because omega 2 minus omega 1 is taken here. So this will be almost tending towards 0. And so you can say in this condition this omega A will be much greater than omega m. Omega A will be much greater, or in other words omega m is much smaller than omega A. Okay, so when we consider that omega 1 and omega 2 are almost equal, in that very condition this omega m will be much smaller than omega A. Okay, actually in this case the modulated amplitude AM and the modulated phase constant delta m will vary slightly with the time, very slightly, as you can see. Since omega m is now very small, almost 0, okay, so when you will take it 0, then cos 0 will be 1 and AM will be completely time independent. This will be completely time independent. Okay, and in the similar manner you can see since omega m is now very small, so this delta m will vary with time, but this variation will be very slight. Okay, so for a time being in this condition you can take that this AM and delta m are almost constant, almost independent of time under the time limit or under the time scale which we will consider. Okay, so I have written it here. You can see the amplitude AM and modulated phase delta m vary slightly with time and hence can be treated constant during the time scale of interest. Okay, and so if now this delta m is almost time independent, omega m is also time independent, so in this condition you can see this AM and delta m may be treated as a constant. Okay, and therefore x equal to AM cos omega AT plus delta m. Now this equation will represent a simple harmonic oscillation because its amplitude AM and the phase constant delta m are constant, not time dependent. But this will happen only when you consider that omega 1 and omega 2 are very close to one another. Okay, only then such situation will occur. Okay, so I have mentioned in this condition equation 5 will represent an almost harmonic oscillation at the angular frequency omega. So now you can say that after the superposition of two simple harmonic oscillations which differ in frequency slightly, we get a resulting simple harmonic oscillation whose frequency is equal to the average value of the individual frequencies. Okay. Now, you can see that the amplitude AM, which has been defined in this equation 6, that varies actually with time t. Okay, in actual problem, this varies with time t. So how it will vary with time t? Now let us see. If you want to find that what are the times at which this AM will be maximum and what are those times at which AM will be minimum. Okay? What are those times? You can see this equation 6 seriously. AM will have a maximum value when cos of 2 omega mt will be maximum. Only then AM will be maximum. Okay? So you can see I have written the resulting amplitude AM, which has been defined like this. This will be maximum. AM will be maximum when cos of 2 omega mt is maximum. And what is the maximum value of cos 2 omega mt? This is, equal to plus 1. And so when this cos 2 omega mt is equal to plus 1, what will be the maximum value of AM? You can write it. The maximum value of AM, this will be simply equal to A1 plus A2. So sum of the amplitude of individual oscillations is the maximum amplitude of the resulting oscillation. Okay? But our prime aim here is to find those time at which the resulting amplitude is maximum. Okay? And for this you have seen the mathematical condition is this cos of 2 omega mt should be equal to plus 1. But if cos theta is equal to plus 1, the general value of theta is 2n pi, where n is equal to 0, 1, 2, 3, 4 and so on. Okay? But what is omega m? You have seen earlier that this 2 times of omega, 2 omega m is equal to omega 2 minus omega m. You can see 2 omega m is equal to omega 2 minus omega m. You can see it here. See it here. Omega 2 minus omega m from here, this will be 2 omega m. Okay? So instead of that 2 omega m, now we write what? We write omega 2 minus omega 1. Okay? And omega is equal to 2 pi nu, where nu is the frequency measured in hertz, or you can say regular frequency. So instead of omega 2 minus omega 1, you can write 2 pi times nu 2 minus nu 1. Okay? And that is equal to 2n pi. And here this 2 pi and 2 pi will cancel out, and therefore t is equal to n over nu 2 minus nu 1. Okay? So these are the values of time at which the resulting amplitude AM will have a maximum value. Okay? That is, its value will be equal to A1 plus A2. Now, after substituting the different values of n, which are 0, 1, 2, 3 and so on, you can get all those times at which the amplitude will be maximum. So t will be equal to 0 when you take n equal to 0. When you will take n equal to 1, then t is equal to 1 over nu 2 minus nu 1. Taking n equal to 2, t will be equal to 2 over nu 2 minus nu 1. Taking n equal to 3, we will get t equal to 3 over nu 2 minus nu 1. So these are the times at which the resulting oscillation will have maximum amplitude, and that will be equal to A1 plus A2. Okay? So you can see the first maxima will occur at t equal to 0. Then the second maxima will occur at t 1 over nu 2 minus nu 1. Third maximum will occur at time 2 over nu 2 minus nu 1. And fourth maximum will occur at time 3 over nu 2 minus nu 1. So if you want to find the time interval between the two successive maxima, you will see that the time interval between any two successive maxima is equal to same, that is constant. So the time interval between first and second maxima will be 1 over nu2 minus nu1 minus 0, and the time interval between the second and the third maxima will be what? That will be 2 over nu2 minus nu1 minus 1 over nu2 minus nu. But all these will be equal to 1 over nu2 minus nu1. So the time interval between two successive maxima is constant, and that is equal to 1 over nu2 minus nu1. So you can say that this delta t is the time interval during which the amplitude becomes maximum one time. So how many times the amplitude becomes maximum in this time interval delta t? Answer is 1. In this time interval delta t, the amplitude becomes maximum one time. Okay. So per second, what will be the number of maximum? Number of maximum created or produced per second is called actually the frequency of maxima. Okay. So the time interval delta t between two consecutive or successive maxima you have obtained is 1 over nu2 minus nu1, and the frequency of the maxima, which means the number of maxima produced per second, since in delta t time maximum is produced one time. So in 1 second, how many maximum will be produced? This will be 1 by delta t. And the number of maximum produced per second is called frequency of maxima. That is denoted by the symbol nu b. And so nu b will be equal to 1 over delta t. In other words, you can also say that the frequency of maxima is simply equal to reciprocal of the time interval between two consecutive or two successive maxima. But you have seen that this delta t is 1 over nu2 minus nu1. So 1 over delta t will be simply equal to nu2 minus nu1. So it is a very interesting result that the frequency of maxima is simply equal to the difference of the frequencies of the two superposing oscillations. Okay. So taking the difference of the frequencies of two superposing oscillations, you can find the frequency of maxima. Now in the similar manner, you can see the same results for the minima. That is, now we are going to see to find all those times at which the amplitude AM will become minimum. Again you can see the expression for a resulting amplitude. It will be minimum when cos 2 omega mt will be minimum. But you know the minimum value of cos theta is equal to minus 1. So minimum value of cos 2 omega mt is equal to minus 1. If cos theta is equal to minus 1, what is the general value of theta? You know, general value of theta is 2n minus 1 into pi, where n is equal to 1, 2, 3 and so on. You may also write theta equal to 2n plus 1 into pi, that is even multiple of pi. Okay, sorry, odd multiple of pi, odd multiple of pi. But when you will take theta equal to 2n plus 1 into pi, then you have to take n equal to 0, 1, 2, 3. You have to include 0 for the value of n. But when you will take the odd number by 2n minus 1, then n will be started from the value 1. Okay. So in this condition, you can see this 2 omega mt is equal to 2n minus 1 into pi, where n has been defined like this. Again, you can see that this 2 omega m is equal to omega 2 minus omega 1. Okay. So this is your result. Now, omega 2 minus omega 1, this can be written as 2 pi times nu 2 minus nu 1, and that is equal to 2n minus 1 into pi. Now this pi and this pi will cancel out, and the time t at which the resulting amplitude am will be minimum, that will be equal to 2n minus 1 over 2 times nu 2 minus nu 1. Now after putting the values of n, you can get all those times t at which the resulting amplitude will be minimum. So let us take the first value of n, which is 1, and this will be actually t equal to 1 over 2 times nu 2 minus nu 1. Okay. When you will take n equal to 2, then this will be 3 over 2 times nu 2 minus nu 1. Okay. So in this way, we get that at time t, at these times, the resulting amplitude is minimum. Again, you will see that the time interval between the two successive minima or two consecutive minima will be constant, and that will be same as that the time interval between the two successive maxima. Result will be same. For this, let us see what will be the time interval between the first minimum and the second minimum. You can see, for getting this, we will subtract this time interval 1 over 2 times nu 2 minus nu 1 from 3 over 2 times nu 2 minus nu 1. And for getting the time interval between second and third minimum, you will subtract this 3 over 2 times nu 2 minus nu 1 from 5 over 2 times nu 2 minus nu 1. And after simplification, you will get that this time delta t is same as you have obtained in case of maxima, and this is 1 over nu 2 minus nu 1. So this is the time interval delta t in which the resulting amplitude becomes minimum one time. Okay, and therefore again the frequency of minima, that is the number of minima occurring in 1 second per second, that will be 1 over delta t, and that is equal to nu 2 minus nu 1. Okay. So now you can see that between any two maxima there is a minima, and the periodic variation of amplitude of the motion resulting from superposition of simple harmonic motions of slightly different frequencies is known as the phenomenon of beats. This alternate variation of amplitude of the oscillation, this is called actually beats. Actually, one maximum of amplitude followed by a minimum is technically called a beat. Now, this time interval delta t, which is the time interval between the successive maxima or successive minima, which is actually reciprocal of the difference of frequencies of the superposing vibrations, that is called actually the beat period. This is beat period. And reciprocal of this beat period, which will be actually nu 2 minus nu 1, this is called beat frequency. Okay, this is called beat frequency. Actually, this beat finds its application in the problem of waves. When you will talk about in our forthcoming videos about the sound wave, we will again discuss these beats in case of sound waves. Actually, in case of wave, you know that intensity of the wave is proportional to the square of the modulus of its amplitude. So here, since AM varies with AM, which is resulting amplitude that varies alternately, that varies periodically after a particular interval of time, which is 1 over nu 2 minus nu 1, this value of AM is repeated. But in case of wave, when you say that the intensity of the wave is directly related to amplitude of the wave. So in case of wave, we simply say that the intensity of the wave varies alternately, and that phenomenon is called bits in case of waves. Okay, but those things we will see later on in our forthcoming videos. So I think this problem of superposition of two collinear simple harmonic vibrations of different frequencies and the concept of bits is now very clear to you. Okay, thank you very much.